So, welcome back to lectures on engineering mathematics 2, and today we will begin with module 3 on numerical analysis. So, this is lecture number 21 on iterative methods for solving system of linear equations. So, starting with the introduction to the iterative methods for solving system of linear equations, we will basically discuss in detail two methods. One is the Jacobi iteration method, the other one is the Gauss-Seidel iterative method. So, these two are the classical iterative methods which we will derive today in this lecture. So, just to begin with, to remind the consistency of a linear system, which was also discussed in engineering mathematics 1 in the section of linear algebra. So, here we are talking about, let us say, the system of linear equations having m equations n unknown. So, this A, the matrix A having dimension m cross n. So, there are m rows and n columns. Similarly, this vector x here has n rows, and then similarly this vector B has m rows there. So, we have this A m cross n and then n cross n, this vector x, and then this vector B having the m rows. So, now if we have the case here m equal to n, what happens? We call this as a balanced system. When m, so the number of equations are greater than the number of unknowns, then we call such a system as overdetermined system. And the third case, when m is less than n, so the number of equations are less than the number of unknowns, then we call such a system as underdetermined system. So, just to recall that for a balanced system, when we have the same number of equations as the unknown, here this k denotes the rank of a matrix. So, the rank of A equal to rank of this augmented matrix A B. So, B is just augmented next to this matrix A. So, if the rank of the matrix A equal to this rank of matrix A augmented B, and if this rank is equal to n, then we have the case of unique solution that was well discussed in linear algebra. The second possibility, when these two ranks, so the rank of A is not equal to the rank of A B, rank of augmented matrix A B, then this was the case of no solution. And the third possibility, when these two ranks are equal, so rank of A equal to rank of A B, but this number is less than equal to or less than n. So, in that case we have infinitely many solutions of the given linear system. The second, now we have the overdetermined system. Again we have the possibility of having a unique solution. That means, if this rank of A equal to rank of A B and this number is equal to n, then we have the case of unique solution from this overdetermined system as well. And when these two rank are not equal, so the rank of A is not equal to rank of A B, then this is the case of no solution. And the third possibility we have, when these ranks are equal, but it is again less than equal to n, it is very similar to the first balanced system, then we have again the case of infinitely many solutions. So, for overdetermined system also we can have the possibility of unique solution, no solution, and infinitely many solutions. The last case where we have the number of equations less than the number of unknown, that means this undetermined system. In this case we have two possibilities, either this rank A is not equal to rank A B, in that case we have no solution, but when this number is equal, rank of A is equal to rank of A B, and naturally that rank is going to be less than n, because the rank cannot be greater than m or n. So, it should be less than m, maximum of m and n. So, when the rank of A is equal to rank of A B, it has to be less than n. So, it is eventually the case which we have discussed for infinitely many solutions for balanced and over determined system. So, here also when this rank is equal, we do not have to say less than n, because which is obvious. So, in this situation we have again infinitely many solutions. So, this is the overall tree for a general linear system having the equal number of equations as the unknown. Here the number of equations are more than unknown, and here the number of equations are less than the number of unknowns. And in each case we have seen the possibilities of having unique solution, no solution, and in the last case undetermined system we have two possibilities, that there will be no solution or infinitely many solution. Here we cannot have the situation of unique solution, because number of equations are less than the number of unknowns. So, we can always assign some free variables in case there is a solution. So, there will be no possibility of having unique solution in that case. What we are going to discuss now, the iterative methods. In this course we are restricting ourselves to this balanced system. So, when the number of equations are equal to the number of unknowns, and that too the situation when we have the unique solution. So, only this case will be discussed now, for the balanced system when we have the unique solution. In that case we will discuss now how to find the solution using the so called iterative methods. So, let us discuss the solution for this system A x is equal to b, where A is n cross n matrix, x is a column vector of dimension n cross n, b is again a column vector of dimension n cross n. So, we have n unknowns, n equations, and then we assume that the system is having a unique solution. So, what are the possible solution methods for such a system? We have naturally the so called direct methods, which, and we have here the iterative methods. So, broadly there are two categories, one we call the direct methods, another one we call as iterative methods. In the category of this direct methods, we have Cramer rules, which the students are familiar with. We have the Gauss elimination method, which was discussed in linear algebra engineering mathematics 1, and we have the Gauss Jordan method. So, again similar approach, and we have also many other the so called decomposition methods, etc. So, it is a long list, will continue, and in this category when we are talking about the iterative methods, the two well known classical methods are the Jacobi method and the Gauss-Seidel method. We have many more. Some of them are like conjugate gradient method, conjugate residual method, etc. So, it is again a long list for iterative methods, some of them are listed here. What are the characteristics of this direct methods? They deliver exact solutions. So, that is the beauty here, in the absence of rounding of error, they deliver exact solution of the given system, like whether it is a Cramer rule or Gauss elimination, Gauss Jordan, and many decomposition methods. So, they deliver exact solution, but there might be approximation due to rounding errors, etc. Whereas, the iterative methods, and that is the difference between the two category, here they deliver approximate solution. So, here there will be a sequence of solution which we will be obtaining, they will be approximating the given system, and we have to stop at some point of time depending on the set accuracy at the beginning. So, here they end up with some kind of approximate solution, and the accuracy will depend how many iterations we are doing to get the solution. Here there was a good point that they provide exact solution, but the drawback here is that they are very expensive, especially when they have they are used for a large system, then it is almost impossible to work with the direct methods, because they are very time consuming, and that is the reason that most of the time for practical problems we go for iterative methods, because they are less expensive, and through these iterations we can really solve a very large system where these direct methods are just restricted to very small systems of dimension 30, 40 or 50 whatever. But when we have the order in thousands or lakhs, then we go with these iterative methods. Well, so before we begin with the derivation of the method, there are some terminologies which will be discussed, which will be used. So, one of them is what is diagonally dominant matrix. A matrix A is called diagonally dominant by rows, and when we call this diagonally dominant by rows, if A I is greater than, so the diagonal entry of the ith row, let us say, is greater than or equal to the sum of all other entries. So, except this j equal to I. So, we are not adding again the diagonal entry. So, except this diagonal entry, when we add all elements, because here the summation is going over this j, the second one. So, if we have the matrix A11, A12, A13, that is a standard notation we use for the coefficients, A23, then we have A31, A32, and then we have A33. So, what we will do for each I, so I corresponds to the rows here. So, I is equal to 1, for instance, we have I is equal to 2, we have I is equal to 3, and so on. So, for each I, if we add the elements absolute value except the first one, now here in this case, here we will leave this and add A21 and A23 as per this notation. Here we will add A31 and A32. So, if the diagonal entry has larger magnitude than the rest, then we call diagonally dominant by rows. Where while it is called diagonally dominant by columns, it is the other way around. Now, if we go with the columns, the first column, the first entry A11 should be greater than, when we add all other elements of that column, if it is greater than equal to the sum here, and that we have to do for each I. So, I equal to 1, 2, 3 and so on, for A22, then A33 and so on. For all these, this has to be fulfilled. So, for each column now, we will check this for each. In fact, better to write here A j j and then put here j is equal to 1, 2, 3 and so on, because the matrix here going to be now A11, A12, A13, A21, A22, A23 and A31, A32, A33. So, the first column we will pick, and then we will check whether the first entry is greater than the sum of the absolute values of the last two. Then in the column 2, so j equal to 2, we will check again whether this and this sum is greater than is less than this value here, and similarly we will check here whether this element here is greater than the sum of the absolute value of the first two. So, we will go with the column wise. So, let us say here A j j is greater than I equal to 1. So, we will sum in this direction for j equal to 1, then for j is equal to 2 we will sum, and j is equal to 3 we will sum all these. Well, so if the above inequalities hold in a strict sense, then A is called strictly diagonally dominant. So, if we have greater than equal to, we simply call diagonally dominant respectively by columns and rows, but if these inequalities are strict, then we call strictly diagonally dominant. So, that is the one definition we will be using in following lecture or in this lecture. Another terminology we are going to have it is a matrix norms. So, just a brief, very brief introduction, the details are not provided here. So, it is just to use these terminologies in this numerical analysis portion. So, this is a number basically associated with a matrix that is often requires analysis of matrix based algorithms. So, here also we are talking about now the matrix and these iterative algorithms based on the matrices. So, here this number which is called the matrix norm, it is a very useful for defining, for instance, the convergence, etc., that slowly we will discuss. So, this matrix norm gives some notion of the size of a matrix, because it is a number associated with each matrix. So, we can, for example, compare two matrices in this sense, or we can find the distance between the two matrices, how, whether they are close to each other or they are very different from each other. So, those notions can be also captured with this matrix norms, which we are going to define now. So, some example of the matrix norm, because there are many ways to define a matrix norm, but some of them are very popular one, very standard one we will state here. Suppose A is a n cross n matrix, then one is called the Frobenius norm, which is defined as in this way. So, we will square each element of the matrix and then take this square root. So, this is called the Frobenius norm. So, this is naturally going to be a positive number, which we are denoting by this norm A. This is the notation for the norm, and F stands for Frobenius. Row sum norm, the other one is the row sum norm, as the name suggests that we will sum each row and we will take then the maximum among these numbers. So, each row, the sum of each row of the absolute value, the sum of the absolute value of each row will give a number, and then we will find out what is the maximum among these numbers, that will be the row sum norm. Or we have the column sum norm, where we will sum now each column, and then among these values, the sum of each column, the absolute value of each element in a column, that the maximum will be searched, and that is going to be now the column sum norm. So, only these three norm at this moment we will just state, and later on perhaps we will go a little more into the details. So, these are the numbers associated with a matrix, which are called Frobenius norm, row sum norm, and the column sum norm. Now, coming to the iterative methods. So, a method for solving linear system A x is equal to b is called iterative. If it is a numerical method computing a sequence of approximate solutions, it will compute a sequence of approximate solution, this x k, we are denoting this x k, x is a vector which is the solution of this system here, and x k is the sequence which is approximating this x. So, x 1, x 2, x 3 and so on, and in such a way that should converge to the exact solution. So, if we keep on going with the sequence, finally our solution should go to x, to the exact solution, as basically the number of iterations goes to infinity. So, such a method, when we have a sequence of the solutions, those sequence are actually the approximations of the solution of the given system, and if such a sequence goes to exact solution, or this is what we call converges to the exact solution x as the iteration goes to infinity, then we call that this is a iterative method. In many cases this sequence may not converge to x, and that is also a part of discussion, that under what condition this method actually particular method converges to the actual solution of the system. So, what is the idea? This is the general idea of deriving an iterative method. This is a very general approach here, but we will go for specific cases in next slides. So, consider for this system of linear equations A x is equal to b, having this n cross n size of A and respectively the n cross 1 and n cross 1 size of B. So, the idea for this iterative scheme is based on the splitting of the matrix A. So, we split this matrix in some kind of these matrices. So, matrix P minus the matrix n is giving us this A, and in such a way that P is a non-singular matrix. I mean, depending on this splitting we will have a different numerical methods, but overall in each of these iterative methods we will do some kind of splitting in such a way that this one matrix, this P, is a non-singular matrix. So, given the equations A x is equal to b, what we will do, A we have written as p minus a n x equal to b, or we can have this p times x is equal to n x plus b. So, we formed here another equation where we have p x. So, the x is sitting left hand side, x is also sitting right hand side, and we know that the p is a non singular matrix. So, that we can invert it and having to have this x completely one x to the left hand side and the rest goes to the right hand side. So, having this p x is equal to n x plus b from the given a x is equal to b, what we do now, we can consider the iterations with a suitable guess. Yeah, that is another point here. For each iterative scheme, we have to also choose initial guess or initial solution to start with, and that is what we call this x 0. So, this p x k is equal to n x k plus b, this is what. So, the left hand side of this x we have kept here the k plus 1th iteration given the values at this kth iteration, and that is exactly the point where how we define the iterations. Here the equation was p x is equal to n x plus b. Here the x, this x will satisfy this equation exactly. So, when x is an exact solution, naturally this p x is going to be n x plus b, because this is the given a x is equal to b. So, if we have a vector x which satisfies this equation, that is naturally the solution of the given system of equation. So, having this p x is equal to n x plus b, what we do, we supply here the right hand side some known solution starting with x 0 and then compute n x plus b, and then if this is equal to this p times x power k plus 1, and in this way we search for what is the x k plus 1. So, the value expected the improved value, or let us first look at this. So, this p is the invertible matrix. So, we have instead of writing this p x power k plus 1, not power, it is a notation. So, k plus 1 n x k plus b. So, we have written finally in this form that x k plus 1 is equal to g x k plus x b. So, given a value here of this x k, we will compute this g x k plus h b, and that we will call this number as x k plus 1, because substituting some value of this x k there, g x k plus h b is not giving, will not be the exact solution, because the exact solution will be g x plus h b. When we give here the exact solution, then only we will get here x. This is the given system of equation, but what we are doing here, we are putting some other value x k. So, we have to start with, for example, x 0. So, we will first give here x 0, we have to start with, and then add this h b there, multiply this with this g, and this we will call, okay, this is our x 1. So, which is supposed to be a better approximation than what we have chosen at the beginning, and then this x 1 we will substitute there, and then we will get a new one, and so on. So, in this way we will proceed with the algorithm. So, this g here, which is p inverse n, this is a very important matrix, the so called iteration matrix, because the convergence of these schemes will depend on this iteration matrix, and then here we have this h as just simply p inverse, which is coming from there. So, what is important here, we have rewritten our system into this form, the x is equal to this g x plus this h b form. This is our system, a x is equal to b is written in this form, and from this we have set up a iteration that provide there some values of x and then compute g x plus this h b, and whatever we get this number, let us set to the values at k plus 1 at iteration. And in this way, when we iterate this, we are supposed to go towards the actual solution, and this g plays a very important role, which is called the iteration matrix of the given scheme. So, now just a few more definitions for the convergence. We are talking about the convergence of an iterative method. An iterative method is said to converge if for any choice of initial vector, the sequence of approximate solution this x k converges to the exact solution, then we call that the iterative method converges, is said to converge if for any choice of the initial vector x naught, the sequence of approximate solution converges to the exact solution x. And the definition of the error, because we will be also talking about error, we call the vector r k b minus a x k the residual, or respectively the error. Error is defined as x k minus x at the kth iteration. So, here there are two type of errors. One is the residual, which is b minus a x, because b minus a x is supposed to be 0 if x is the exact solution, because a x is equal to b is our system, but this is not 0 for those approximate solutions. So, we can have actually we can define I mean this gives a notion of the error itself, and this is called the residual at the kth iteration, or the actual error is actually x k minus x, but since the actual solution x may not be known. So, this is this may not be used, actually this error may not be computed, because here we need this actual solution x, but this b is known, a is known, and x k is the approximate solution. So, we can readily compute this b minus a x k, and that will give actually the notion of the error, which is called the residual. Just a remark, in general we have no knowledge about this E k, because the exact solution x is unknown. However, it is easy to compute the residual, this r k. So, the convergence normally is dedicated to the residual in practice. So, when we talk about the convergence in practice, we check whether this b minus a x k is close to 0 or it is going towards 0. So, this is based on this residual only. Now, coming to the Jacobi iteration method, if we consider the system A x is equal to b. So, here now we can derive this particular type of iteration method. So, take this splitting of this A as A is splitted into L plus D plus U. Here we call the lower triangular matrix, this is the D is the diagonal entries of A. So, the diagonal matrix, and U is the upper triangular part of A. So, if we have this type of splitting of A, the lower portion here below this diagonal we call it L, and then here we call this U, and the middle one is the elements of the D. So, this is lower triangular having these elements L, and the rest will be set to 0. In D, only this D 1, D 2, D 3 and D n will be there in the matrix, rest everything will be 0. In the upper one, we will have this upper entries of the matrix, and the rest everything will be set to 0. So, having this splitting now, A is equal to L plus D plus U, what we do? A x is equal to b can be written now in this form, L plus D plus U x is equal to b. That means, now we take the d with the x and the rest everything to the right hand side. From here we will set up the scheme. So, we have d x is equal to minus L plus U x is equal to b, that is our equation, and assuming that D inverse exists, because D are the diagonal entries. So, assuming that the D inverse exists, we can write down x is equal to minus D minus 1 the D inverse L plus U x and D inverse b. From here now we can set up our scheme, that the left hand side we can put the values after k plus 1 iteration given the values at kth iteration. So, the iteration method is given by this scheme now, x k plus 1 is equal to minus D inverse L plus U x k plus this D inverse b. This is the so called the Jacobi iteration method. The only important point here is that A was splitted in this form, and the D was taken for this inverse to the right hand side, and we have this relation for x, actual x, and then for approximate x applying here we are getting the new value of x k plus 1. So, in component form, this we can also write in component form, because this is written in matrix form. So, this is the matrix form, but we can also write in component form. So, component form means that all these unknowns x 1, x 2, x 3, x n, we have n unknowns. This is exactly coming from this matrix form itself, this D inverse, because this was the diagonal entries. So, only this 1 over I aii element will come here, and D inverse B again. So, this B I will come, the D inverse is already sitting there for the ith row. So, B I, and then this here L plus U. So, except this the diagonal entry, the rest are summed up. So, A I j with this x j, the kth one. So, we will discuss this a bit more in the next lecture. So, there are two forms, one is the diagonal form, another one is the component form. Now, coming to this Jacobi only, this is what we have seen, either this form or whatever this form, they are same form. This we can rewrite here, this one we can rewrite as 1 over a I b I minus this summation we have split it into 2, because the j is not equal to I, we are not considering the ith entry there for the sum when j is equal to I. So, basically what we are doing when the sum is up to j less than I, and then the sum is for j greater than I. So, this we can also rewrite in this form, and this is exactly the point. Now, we can derive the another method, Gauss-Seidel method, which is usually or supposed to be a better approximation than the Jacobi method. What we do in the Gauss-Seidel method, here this all values of x are kept as kth iterations, and then all values of this xi's x 1, x 2, x 3, x n, they are computed at k plus 1th iteration. So, all the values here of the previous iterations are used in the right hand side to compute the new values. What is the idea of the Gauss-Seidel method? That newly computed components. So, whenever we have computed, for instance, here x 1, this x 1 should be used there instead of the values from the previous iteration. When x 1, x 2 is available, so then we should use these x 1, x 2 to get x 3, for instance. So, this is the idea of the Gauss-Seidel. So, this scheme basically becomes that whenever j is less than I, we will be using these computed values, and j greater than I we will obviously use from the previous iteration. So, that is the only difference in these two. Here the kth values are used, here k plus 1th. So, newly computed values of x are used in the algorithm. So, we have this is the Gauss-Seidel method, and in matrix form again we can write this. So, this will be for to compensate this d 1, then we have this for b, and then here this is the lower part of the matrix is used here. So, L x k plus 1, and there you have u x, the values are used here at kth iterations. And now, we can just do a bit more simplification. So, here this L can go to the left hand side. So, we have d plus L. So, first we will multiply by d there. So, we have d x, and here plus L x is equal to this one, and then we can invert it. So, finally, in the matrix form we have this algorithm that x k plus 1 is equal to minus d plus L inverse, and the upper triangular matrix x k and d plus L minus 1 b. So, there is only slight difference in the Gauss-Seidel method than the Jacobi method, that in Gauss-Seidel we are using the recently computed values, and as a result this matrix form takes this form where d plus L inverse u, and here d plus L inverse b is coming. So, this is the iteration matrix for the Gauss-Seidel method. Well, so these are the references we have used for preparing this lecture, and in this lecture we have introduced the idea of the iterative methods, and in particular we have derived the Jacobi method and the Gauss-Seidel method, and they slightly differ from each other at this expression here. So, the values of x, the recently evaluated values are used, and in this case all the values from the previous iterations have been used for the computation of the new values. Well, so that is all for this lecture, and I thank you for your attention.